Welsh water tunnels. Presented today by Jamil and Puneet from Headline AI, and it's quite an interesting tool. Looking forward to it. If you do have any questions, please can you just use the chat window at the bottom and just type the questions in, and we'll go through them one at a time. Just to try and organise it, we'll try to put everybody on mute for the speakers. Jamil and Puneet, over to you guys. Thank you.
Thank you very much. So hello everyone, my name is Jamil Marafi, and today I'm going to present along with Dr. Puneet Shabra on our winning entry for the Utility Pipeline Technology Award. So thank you for the opportunity for allowing us to present. This was a joint entry with Wessex Water and Bright Innovations Group on Telesto 3D LIDAR modeling of tunnels in semi-turbulent flow. So Telesto is a product that has been in R&D for nearly 3 years now. Today we're going to give a brief introduction to why inspecting subterranean infrastructure is important and some common methods currently employed. We'll then move on to discuss our solution, Telesto, give some background on how it was developed as well as its capabilities and limitations. And then we'll then go on to a recent case study with the Bournemouth CIS. Towards the end, we will introduce some other areas we're currently working on and some future work. So including new AI models and analytics, as well as predictive maintenance and how it can be used for advanced planning. So a little bit about us at Headline AI, we conduct sensing and data processing across extreme environments with a focus on GPS denied locations and those with low visibility, such as subterranean infrastructure. So we believe subterranean infrastructure is vital for our modern civilization, and it's critical for water and wastewater supply, electricity supply, gas supply, communications networks, in construction, for buildings, foundations, and also for underground transportation. However, underground infrastructure remains challenging and expensive to monitor, and the work is often described as dirty, dangerous, and dull for workers. Many countries are also experiencing an aging infrastructure problem, which is really only being made worse through climate change and increasing urbanization. So it is important to regularly inspect water and wastewater assets, and utility companies need new cost-effective tools to do so. To ensure efficient operations for all of its customers, to ensure health and safety for the public, to prevent catastrophic failures such as structural collapse or environmental contamination, to limit costs, especially large capital expenditure and reactive maintenance costs, also for insurance of their assets, and to accurately locate assets for maintenance, rehabilitation, and construction purposes. So locating underground assets is really critical across several industries, but especially important for utilities, rail, and construction. So in a recent geospatial publication, it was claimed that 90% of underground utility damage during construction is attributable to incomplete, inaccurate, and out-of-date records. So this is not really surprising, as it is extremely challenging to determine basically the exact location of underground infrastructure without significant effort, especially as location really needs to be known to an accuracy of within about 0.5 meters or better in X, Y, and Z coordinates. So for maintenance and for rehabilitation purposes, but also to prevent damage to utilities during construction works. So this map provided by Wessex Water shows the location of some underground assets in relation to what is above ground, which is really critical to construction projects and urban development. So prior to construction, the assets need to be accurately geolocated in X, Y, and Z coordinates, really to avoid expensive mistakes during construction. However, determining the accurate location typically involves expensive surveying techniques and therefore really remains limited, reliable, up-to-date location information on many underground assets. So understanding the condition of underground assets over time is really vital for maintenance and rehabilitation works. Many subterranean assets are prone to accelerated aging and loss of structural integrity. This is because the building materials are exposed to really harsh conditions, such as extreme moisture, hazardous and corrosive gases, also repeated high and low temperatures. As can be seen in this photo on the right, these places really are dangerous places for workers and for the general public too, if the condition actually deteriorates and are not regularly monitored. So for this reason, it is really important to monitor cracks, deformations, and other defects that form over time. So one method that is commonly employed in the industry is to conduct inspections using CCTV surveys. So this typically involves at least a two-person team, a CCTV robotic crawler system connected to a power line, and various safety equipment. It normally requires a NC2 confined spaces entry to really place the robotic crawler into the structure. And then the crawler is driven by one person who controls it from the van parked near the manhole access point. So CCTV footage is recorded and defects noted manually using industry standard notation. So CCTVs are an established method, generally fast and low cost, which really works well for condition assessment of many pipes. But however, the method generally struggles with larger structures, so ones that are greater than 1 meter in diameter. It provides limited location and structural assessment information, and it's manual and subjective. An alternative method to assess these assets is through 3D laser surveys. These are great at producing dense point clouds with high absolute location accuracy within millimeters or centimeters type of precision. So as they utilize these like survey grade type of laser scanners and deploy calibration targets. So these calibration targets are placed within the underground environment by surveyors who need to traverse these kind of environments and take multiple scans at different fixed positions. So this makes them ideal in terms of a structural assessment. However, they are really prohibitively expensive for most situations, mostly avoided unless absolutely needed. This is because they involve significant planning and resources. They require an NC3 or an NC4 confined spaces entry, and several teams are often needed to conduct the operations and minimize the health and safety risks that are posed. As we saw in the earlier slide, sewers can be really hazardous environments. So this is really essential that they have all these teams. Another downside though is the data collection and analysis process can be extremely time consuming and sometimes taking months to really plan and execute these types of projects. So after having some conversations with Wessex Water and the wider industry, we really understood that health and safety was a priority. Wessex Water still needed to survey large tunnels and critical assets accurately and for structural assessment, but really they want to avoid putting people into such environments, into these types of tunnels and other hazardous environments. So they have, of course, utilized 3D laser scanning to produce 3D models and dense point clouds of some of their structures. However, they have over 100 kilometers of large diameter, up to 5 meters in diameter tunnels. So and a lot of these are really inaccessible, some as much as 90 meters deep, with access points basically every 1,000 meters or so. So it's important to really, for them to understand the effective stress changes on these assets over time, and really how best to spend on maintenance and rehabilitation programs. Essentially, they need to know what are the most deserving assets. So after searching the market for solutions, we found a few alternatives. There is laser profiling, there is sonar surveys as well for below the waterline. But it was really above the waterline that utilities seemed most interested in. Previous attempts to implement LIDAR, especially in semi-turbulent flow conditions, had failed. But with this, we were up to the challenge, and this is something that we really wanted to try and achieve. So I will now proceed to give a brief introduction to our solution. So that is called Telesto, and how it's been developed over the last 2.5 years, basically through intense R&D and collaboration. So Puneet and I started Headlight AI back towards the end of 2017. We initially started experimenting on using sensors on a skateboard and actually in a local tunnel in London in a place called Bournemouth back in early 2018. So we then developed the system to basically operate on a wheeled robot and produce our first 3D mapping software, which could generate 3D, but also determine material and surface types, very important for condition assessment, as shown by the different colors within this processed point cloud. We then conducted a technology trial in collaboration with OnSite, where we implemented our solution on one of their wheeled robots. On the right, you can see a video that shows the point cloud that we had generated using our software. In the image here, you can also see the cracks that were identified in this culvert from the LIDAR imaging technique. So this did not utilize any cameras. This was purely based on LIDAR. The deformations of the culvert could also be then objectively analyzed. And this feature will be highlighted by Puneet later on in the webinar. As part of the United Utilities Innovation Lab, which we're a part of, we could also show a comparison of traditional CCTV footage compared with our virtual fly-through using our new LIDAR method. The low visibility in the CCTV footage is another issue with just utilizing cameras for inspection. The various colors in this point cloud represent different surface properties or materials again. So it was all very well us producing 3D maps of dry tunnels with wheeled robots, but most large critical assets have flow in them, and sometimes it can even be turbulent conditions with fast flow of water or wastewater. So this presents a very different challenge to mobile LIDAR mapping. So yeah, what about tunnels with turbulent flow? So we started technology trials with Wessex Water, who had highlighted this to be an unsolved problem in the industry. We built a new prototype system with LIDAR and inertial sensors, and then basically experimented with various parameters on both the hardware and the software, ensuring as well that the system could cope with the large amounts of data that generated. Often it's around gigabytes per minute that we have to process and pre-processors within the system. So we were also introduced to Bright Innovations Group, who has lots of experience deploying boats in large critical assets. And they ran the operational process of deploying this new system in a major sewer in Bristol back in 2019. So in this trial, we helped show that we could successfully map underground tunnels in 3D and identify specific types of defects from the 3D data. So now I'm gonna hand over to Puneet, who's basically gonna go through some of that initial work.
Thanks, Jamil. My name is Puneet Chabra, and I'm the co-founder and chief technical officer at Headlight AI. As Jamil briefly touched on, we have been working with Wessex and our partners to develop different versions of Telesto. So I'm going to first talk about the version number 1, and over the next few minutes I'll actually take you through some of the features and how we came about building the most latest version of Telesto. So this was Telesto version 1. We started with multiple LIDAR systems. The one with the name to build a photorealistic point cloud on a moving platform. So one of the examples of the outcome is shown on the bottom left. During our deployment, we obviously integrated multiple LIDARs that give us a full 3D point cloud, and the aim was to compensate for the motion. The final deliverable was a web platform for the clients to actually analyze and do virtual fly-throughs onto with the point cloud, but also to help them generate some data-rich reports in the end. We also explored advanced algorithms that allowed us to identify cracks, look at corrosions on the LiDAR imagery alone. So version 1 did not have any cameras. Now, compensating for any form of motion when you do not have any artificial targets or GPS is an extremely challenging problem to solve. And you actually go back to research done in mobile robotics, which is done both on indoor and outdoor applications, but most of these applications either are in very well lit conditions or have got a good GPS signal in them. So just to highlight this problem in a graphical manner, I would ask you to focus at the bottom of the screen. You actually see that is kind of the random motion of the boat that we get. Again, we worked very closely with Bright to understand what controls this motion and sort of what impact would it have on the sensing. The example of this without any processing can be seen on the screen. So the data looks very sparse, and you can actually see the zigzag motion of in the final output as well. So this is was quite interesting at the beginning. Again, there was a lot of back and forth with the client, as well as understanding what was more important here and how do we fix this problem. At the same time, we were also considering options from different other sensors. So Telesto became sort of a multi-sensor system. So how did we fix it? Our solution is a purely software solution. So it's a non-gimbal, no additional hardware. It basically compensates for the motion. So the sensor suite looks for multiple features that we try to track over time. And again, these are all dependent on the environment, the condition of the sewer, the lighting. So there are lots of factors to consider. The localization algorithms then try and take all of this data. Then we come up with an estimate of the position where we are in the sewer. And the sensor fusion algorithms also then try and fuse the data together to produce a dense 3D map. Now, again, this is without any sort of camera, and it does compensate for some motion. That was all great, but we also started looking ahead to see when we've generated this dense data, can we then use it to identify cracks? And here's an example that you see on the top right of what happens before we put them through our algorithms, and in the second row we show the cracks which are identified, and on the right we show the variations in the local geometry of the point cloud, which is primarily due to several reasons, stress, and also could be the earth above pushing inwards onto the pipe or the sewer. So we've tried to identify and see what this variation looks like and give it some color. So that's what you see with those various colors from purple to green, and high variation, you have lots of noise in the color. Bottom was early experiments on understanding where do we have cracks, where do we have side inlets, how can we identify water if it is semi-flooded, for example. So cracks are coded in red, water dripping from the roof or the floor is highlighted in blue. Obviously, it's early days and it was still experimental work. We didn't really stop there. We then went on and looked at what other statistics could be produced, because the aim was to give users more tools that they can build a report which is data-driven and data-rich, and also give them a holistic view of what the entire pipe looks like for anomalies or cracks, for example. So this example is, I'd like you to focus on the image on the left. We've grouped anomalies that we think are interesting to look at, and we've grouped them based on the distance and the type that we believe is an interesting type to be monitored. And then we started looking at the frequency of the occurrence of these anomalies over time or over the length of the pipe. So this allows us to build a holistic view of how many anomalies do we have at every regular intervals. And that's the graph on the right. You actually see the length of the pipe and the areas the user should actually focus on in particular. So this is for the anomalies. We also then looked at what happens to the shape, and again with the same idea in mind to build a holistic view of the whole pipe. We then started looking at some variations in the shape. The culvert that Jamil just showed you right at the start with lots of cracks is one of the most interesting ones, because the earth above was actually pushing in, and you started with a very symmetric shape, and then as you got into the culvert, it became more isometric, and that is highlighted here with the various colors. So red is showing really high variations and the change of shape, whereas blue is more in line with the symmetrical shape that we hope the culvert should be. Again, looking at the frequency of the occurrence of these change of shapes is highlighted in the graph. All of this actually fed into the development on V2. We grew as a team, we got more information from the customer, and we started looking at what were the key pain points. We did have some solutions on the software, we then focused on the hardware. So this is what it looks like at the moment without these lines. This is just to demonstrate a couple of features. We did stuck with the LIDAR. It's great. Again, for the algorithms to pull out cracks, for example. So it does have a 3D vision system which utilizes LIDAR. Operators can connect using Wi-Fi, and this is go through a very simple and a plug and play process of configuring Telesto. It's pretty straightforward. Now this version has got multiple cameras, and these are sort of strategically placed so that we get multiple views, which also assist in the further analysis. It is watertight, and it is housed in an aluminum housing. Again, is industrially designed, and we had to work with some partners to get that done. It does come with a dual purpose carrying handle. It has got plenty of lights. There's lights on the handle. There's forward-facing, front-facing lighting for the forward-facing camera. It is battery operated. You've got plenty of battery, and it's got plenty of storage. So over 2 terabytes of internal storage. It does come with a suite of other sensors on board that allows us to compensate for the turbulent flow that we've been talking about. So the process is pretty straightforward. We hand over Telesto to the operator. The operator deploys it onto a floating platform, or even a wheeled robot if the environment suits it. Once they've configured it, the survey is done. The survey is completed. The data is uploaded to our servers, and we provide a web interface where they can upload the data. We process the data. We perform certain checks on the data, and we provide tools and a sort of a snapshot of what we believe is the condition of the asset, and this is provided through images to point clouds, so annotated data, and some of the graphs that I was talking about earlier. Finally, this allows the operator to submit it to the asset owner with a data-rich report. Here's it in live action. Obviously, this is exactly where we are right now. It's a small snippet showing everything switched on. The cameras are on, the LiDAR is on, and lighting. So I'll now talk about the case study, and this was with Wessex Water and Bright IG. You can actually see Telesto attached to the floating platform, and a very happy customer there. It's 8 kilometers, and it's a mixture of foul and combined sections, but mostly concrete. So we processed it. It's a lot of data, or 0.5 terabyte of data processed both on LiDAR and combined LIDAR and CCTV. Again, users get their own accounts. You use the dashboard, you search for the assets you're looking for, you go to the sections that we've already scanned, and that takes you straight to a 3D point cloud visualization tool. Now, over the next few minutes, I'll show you some examples of what the final deliverable looks like. So traditional CCTV, as Jamil has been emphasizing, is great, but we had to move on. It got one particular view, and not only Telesto's aim was to give you multiple views, but also co-register that data or metadata with LIDAR. So this is an example. You see CCTV on the left. An interesting side inlet there coming in, and you can actually co-register and locate it in the LIDAR. And this is sort of over time sort of builds and creates a digital twin of your asset if you are going to repeat the surveys over time. Another example, so not only just finding them, locating them. Here's an example of a different view. This is a side camera view. We have annotated some parts of these images for sensitive for purposes, so you actually see some of that annotated. The corresponding LiDAR image allows users to actually make measurements, and you can annotate it, take a screenshot, and have it as part of your report. Another example of something with this particular scene is made up of a rag hanging. You have fresh infiltration on the walls, and you sort of find them straight in the LiDAR. Not only that, we can then start measuring the volume or the surface area of that infiltration over time. So it is quite a powerful tool when you sort of combine it with both CCTV and LiDAR. Not only that, this was an interesting element. One section was of the CIS was lined, and obviously it was surveyed before, and we did a post survey, and this image allows you to actually see which going from the old part to the new part, which is repaired, and you can actually start making measurements of what is a change in the diameter, and this could be done over time. So again, building like a more 4D picture of over time of the asset. Also, to emphasize on the different views, this is another example, looking at front view and then finding the same on the side view. This is something that is very different to most traditional approaches. Some of these cracks are from the side view cameras, which would have not been possible using traditional CCTV, and obviously it's a better health check of the asset over time. This is some of the most interesting work that is happening at the moment with the team at Headlights, and this involves using modern AI tools and building custom models to understand what is the condition of the asset. So I would like you to focus on the left image first. This is purely showing us the degree of calcification, and we've color coded it with some heat map. And the highly dense calcified areas are blue, and then you have the other end of the spectrum is red. So it also shows you the distribution of calcification. This is all machine analyzed, so it's not done manually, right? We train a small section of the pipe, and then the rest of the section is tested over using the models. The right is looking at exposed aggregate, and we have started training models on 6 to 7 different kinds of materials and classes, and the analysis is done based on how accurate are these and how repeatable are these over time. So that's the graph on the right. So in conclusion, before I hand back to Jamil, if you have assets underground and you must deal with turbulent flows, think of us and think of Telesto. So yeah, thanks.
Thanks, Puneet. So really to summarize, Telesto combines the best of CCTV and 3D laser surveys whilst improving health and safety. So it provides a complete condition assessment of your large critical assets, 3D maps of your assets with geolocation, improved health and safety compared with traditional LiDAR surveys, significantly more informative than traditional CCTV surveys, It can provide CapEx savings due to enhanced knowledge of which assets should be prioritized for maintenance and for rehabilitation. And it also provides lower risks through improved operations and proactive maintenance. So for us now, ongoing and future work, we're always very happy to collaborate with other organizations. So we would be very keen to work with other utility companies as well to help set a new standard, develop new products as well with universities and robotics companies. We're already working on some autonomy and path planning algorithms, specifically new techniques for localization and mapping. And we're also involved in an Innovate UK funded project called the Prometheus project, which is all about developing underground autonomous drones. And in addition to this, we're looking to further miniaturize the technology so it can be used in smaller pipes, essentially so we can 3D map in X, Y, and Z for smaller structures too. Other structures and of course confined spaces. So with that, I'd like to thank you very much for watching, and we'd be very happy to answer any questions you may have.
Sean, if you can type any questions in the right-hand side in the chat window. Got one so far from Ian. I've got that right, Ian? It's an unusual name. Apologies if I've pronounced it wrong. Does the Telesto output include coding of sewer defects in accordance with the manual sewer condition classification?
Not currently on the LIDAR. Obviously, this is a new technique. However, the video files do not prevent operators from using software that they're also familiar with to label it according to those classifications. So it can, and we are building that feature into the software itself. But at the moment, you can use the video file and of course still do the normal sewer classification as you need.
Cheers, thank you. It was Owen. Apologies for that pronunciation, terrible. One from Norman. Can the system be used on assets of different cross-sectional shapes, or i.e. rectangular?
Yeah, I think, yeah, in theory, if it is deployed on a moving platform, yeah, it can be on, well, it could be on any shapes. We've also done a test on a sort of an egg-shaped sort of a pipe. So whether those are bricks, concrete, so yeah, it should work on rectangular shapes as well.
Just to add to that, at the moment, we're typically focusing on structures that are around a meter, slightly less. It can handle slightly less than a meter. So as long as it's got that kind of dimension within that structure or larger than that, then it should be fine. So it's very good at handling very large diameters as well. On the LIDAR, there may be in some cases some limitations on camera, very large diameters, but of course you're getting that rich information from the LIDAR as well.
One from Kieran, Kieran's actually the innovation manager up at United Utilities. He's put a suggestion there encouraging us to look at pipebots. .ac.uk. Is that a similar tool, or is that like an add-on tool that would help, Kieran? He's probably typing away in the background.
It's another funded program that perhaps Headlight might benefit from collaborating with others. Lots of people trying to miniaturize, lots of people trying to automate. Just another group that there may be some similarities, and that perhaps is just another group to collaborate with, or to consider collaboration. Sorry.
Thanks, Kieran. Yeah, that's we've noted that, and yeah, it's something we're definitely keen on doing as well. So we'll follow that link. Thank you for that.
Thank you.
One from myself. With the survey data you're using, what's the minimum sort of crack identification size you could spot?
So at the moment, again, it also depends on what degree of flow do you have underwater. This particular LIDAR itself, again, most of our wheeled experiments with the wheeled robots, we could identify, or we could understand up to like maybe in terms of the relative accuracy. So we're within 0.5 to 0.7 mil. And again, if the registration is dense enough, then we can identify cracks around that region. I think the version 1 was to understand the limitations of what we would get with LIDAR, especially when it's moving. then we moved on to version 2 to actually see combination of information both from LIDAR and CCTV will potentially enhance the detection methods. So it is still slightly, some of that work is still ongoing to understand if in combination can we improve the detection accuracies of cracks. But in terms of the accuracies on the LIDAR, we densely registered is
I would say it's sometimes a bit position dependent, right? So I would say, depending on the field of view of where that crack is within the structure, sometimes it's around what, 0.5 centimeter. So yeah, like a 5 mil maybe type of crack. But then it could be slightly less than that if it's got a direct view from within the LiDAR. In some positions, it may be slightly more than that. But one good thing is that's part of the reason also why we included cameras, because using the cameras, especially those side or top cameras, we can sometimes see almost like hairline type of cracks, like very, very fine cracks, which obviously sometimes the LiDAR will struggle with picking up. So that's one of the other reasons why we actually introduced CCTV, well, the video as well.
A lot of the imagery was above water level, should I say. Is there anything that you're measuring below water level?
Not currently, but we have capabilities to develop a sonar part of this system as well. There are lots of kind of commercially available sonars on the market that we would acquire to kind of complete this down the line. From what we've seen, and maybe we're wrong, it seemed to us that within the industry there was more of a focus on above the line, and that if the condition was bad above the line, it would be bad underneath. But yeah, it's certainly something that we need to add to make this improved.
Yeah, certainly from my own experience, I'm more on the clean water side, and we have quite a lot of channel flow aqueducts where we try to measure equally below water level as above water level. It's quite a unique use of the product, but it might just double your market sector. That's all I'm thinking.
No,
if it was a clean water solution.
It's a really, yeah, thanks for that. It's a good suggestion. I mean, Puneet, you've had a lot of experience as well with sonar as well. So
yeah, I mean, there were a couple of occasions where we've heard stories where you deploy it on a moving platform, and because you can't see underwater, the platform just sort of falls into sort of a small pit, and that is not good for the LiDAR if you are wanting to switch. So having some form of eyes or ears underwater is quite essential. It is on our development plan, but we also are talking very closely with the customers to understand what are the pain points right now. And obviously, we are still a very small team, so we are open for working with other experts or other companies who would like to collaborate with us.
I was on mute then for a second. Another question from Norman. Can it be used on metallic pipes?
Yeah, metallic pipes. Yeah, it can be. The material of the pipe should not be too much of an issue to an extent, and the size will. Yeah, I guess when it gets very, very small, it could be an issue at very small pipes.
It depends. My answer is depends. From a LiDAR perspective, we have issues with specular reflections. So if those pipes are old and they're not brand new, or they're, again, I'm not an expert here, so if they are painted with non-specular paints, I don't see a problem. But if they are really shiny surfaces, then we may see sections of the pipe, but we may have sections of the pipe which are completely missed.
Is it also from an angle of the initial the kind of IMU units and the magnetic effects of some pipes? Is that where that question's coming from, basically?
Oh, I think Norman's on mute.
Sorry, I've come on muted. Yeah, that's what I was thinking about, really, about whether there was any effect in terms of
I think, on the inertial measurement.
There are non-MEMS kind of IMUs out there, which would obviously make the whole unit quite expensive. Again, it comes down to the point of how regularly are these assets meant to be examined. A, B, what is the scale of this, and is actually, would it make any business sense to actually approach and look at those expensive IMUs? But I was looking, I mean, obviously 3D is interesting. It's not that this LiDAR is the only solution. There are other imaging techniques that give you LiDAR and image as well, which may work and not have the specular reflection effect. So it has to be looked at on a specific case. But at the moment, I think with Telesto, the version we are at the moment, the aim is much larger diameter pipes, but metallic would require some more.
We haven't seen any. We have done bits that are, there's got metallic parts on it, and we haven't seen any issues on the ones that we've done.
They were old.
They were old. But I mean, on the IMU unit, there was no effect on the IMU. So the magnetic effect didn't seem to change it, as far as I was aware.
It is inside an aluminium housing. So there is some piece of.
There is metal.
There is some piece of magic behind that sort of calibrating.
Yeah.
Great, guys. If there's no more questions coming up on the right-hand side, I'll draw it to a close and say, Jamil and Puneet, thanks for a great talk today. Innovative product and quite different from where we were when I started out in the industry a long time ago.
Thank you very much for having us. Yeah.
We've got 4 more talks coming up over the next 2 weeks. We've got R2M on Thursday talking about their innovations going on at the moment. We've got MMB who did a project on the Burnway next Tuesday. I found that Tunnels one next week on Thursday. And then we've got Control Point on the 29th. Basically, they're all listed out on the Pipeline Industry Guild website if you have a look on there. But for today, thank you very much, everyone. Cheers. Bye-bye.
Bye-bye. Cheers. Bye-bye.
Okay. Thanks, guys.